So the next theorem is continuous mapping theorem. So what it means is that if a function g, a measurable function, that's almost continuous, which means that the discontinuous point of g has a measure 0. Um, then let's say then the continuous mapping theorem tells us that if xn converges to x infinity in distribution and the discontinuous point of g has a measure 0 on the random variable x infinity, then the gxn will converge to gx infinity in distribution. And further, if g is bounded, then the expected value of gxn will converge to expected value gx infinity. So that's the continuous mapping theorem. We have a very similar theorem in convergence in probability. So let's go back to there and look at that one as well. So in convergence in probability, we have a theorem that is, where is it? Yeah, so we have a corollary. So if xn converges to x in probability and f is continuous, then we have fxn converges to x in probability, right? So that's and if f is bounded, then we have also convergence in expected value, right? So that's the version in convergence in probability, and we have a similar version in convergence in distribution, and that is called continuous mapping theorem. So to prove that, we're gonna use this Pomental lemma, right? So we're gonna use that. What is that? So let's review that Pomental lemma. It says that if xn converges to x infinity, if and only if every bounded continuous function g, we have g expected of gxn converges to g expected of gx infinity. And it's also the same for Lipschitz continuous, bounded Lipschitz continuous function. So we're going to use that to prove our continuous mapping theorem. So if we want to prove this converges to this in distribution, we want to prove that for bounded continuous function f, we have expected of f compose g xn converges to expected of f compose g x infinity. So then let's let f be any continuous and bounded function. Then the expected then we know that because xn converges to x infinity in distribution, we can construct random variables yn and y infinity that converge almost surely, and they have the same distribution of xn and x infinity. And because it converges almost surely, we know that the composed function of f and g on the yn will converge to the composed function of f and g on with y infinity almost surely. And by the bounded convergence theorem, because it's bounded, we are bounding on a probability measure, so the whole integral is finite, and the function is bounded as well. So by the bounded convergence theorem, which is a special case for dominated convergence theorem, we have this convergence. So that's prove the first part, and therefore we have this converge this in distribution. So the second part is if G is bounded, then same thing by the bounded convergence theorem. The function is bounded, right? So the integral of that function on the xn is just, they have the same distribution. It's just expected value of g on the yn, and that yn converges to expected value of y infinity, which is the same as expected value of g x infinity. So that's that's proved the second part of the continuous mapping theorem.